Hello, Professor Simmons here. This video looks at separation of Laplace's equation in cylindrical coordinates. So let's write out Laplace's equation in cylindrical coordinates. Our potential is a function of r, theta, and z. So z runs along the axis of our cylinder, theta runs along the curving wall of the cylinder, and r, the usual radial variable going out perpendicular to the long axis. The del squared operator in cylindrical coordinates looks like this collection of r derivatives, a pair of theta derivatives with a 1 over r squared factor, and a pair of z derivatives, all acting on the potential. We can rearrange the r derivatives to show that they are in fact a double derivative plus 1 over r times a single derivative, and that will be useful later on. At first glance, this doesn't look so bad. It's a little more complicated than looking at the Helmholtz equation in plane polar coordinates, which we did earlier in the class, because in addition to the r and theta terms, we've added one more degree of freedom. But it's not directly coupled into the others through factors of r and theta, so it doesn't look too bad. And Laplace's equation certainly looks simpler here than in spherical coordinates, where we had all those factors of sine theta to worry about. However, as it turns out, mixing curvilinear coordinates like r and theta with a Cartesian coordinate like z does add a degree of technical difficulty. Well, with that warning, let's go and separate the equation. We make the usual ansatz that the potential is the product of a function of r only, a function of theta only, and a function of z only. We will substitute this into Laplace's equation and divide by a factor of v over coordinate r squared, and the result looks like this. We have a couple terms depending only on the radial variable, a term depending only on the angular variable, and one depending on the z variable with an extra factor of r squared in there. So since the theta variable is isolated completely within this term, we can say, let's focus on that first and replace this piece of the equation by the first separation constant, negative p squared. So for periodic solutions on the range of the angular variable 0 to 2 pi, then the function capital theta of variable theta will just look like cosines and sines of p theta. Very straightforward. We've seen that kind of solution before. Next, let's see if we could take care of the z variable perhaps. So if we go back to our equation, we've got the terms in r. We've now replaced the theta term by just the separation constant. And we see, looking at the z term, that if we divide the whole equation by coordinate r squared, we'll separate off the z term by itself. So let's do that. And now we have a slightly modified version of the radial terms and of the replaced angular term. Here's the z term sitting by itself. We can replace it by the second separation constant, k squared. And now we see that there are two different ways the solution could appear. If k squared is a positive number, then this little differential equation here in z will have a monotonic solution, a solution in terms of purely growing and purely decaying real exponential functions of z. On the other hand, if k squared were less than 0, the solution to this equation would be oscillating. It would depend on sines and cosines of kz. Either is possible. We just need to keep track of which sign sign we are assigning to k squared. Finally, we will need to look at the radial equation, and to do that, we go back to our equation in its present form, and we realize we have the radial terms. We have now replaced the angular term by this simpler form. We've now replaced the z term by this simpler form. And to get a differential equation in r in a conventional form, we'll want to multiply through by the function, capital R, and that's on the next slide. So now our radial differential equation is all that we have left to worry about. We have two derivatives of function r. We have a piece that looks like 1 over coordinate r times one derivative. And then we have these terms that come from the original z term and theta term multiplying r. All of it equals 0 on the right-hand side. This differential equation is known as Bessel's differential equation. So you can immediately conclude that the solutions will be known as Bessel functions. But once again, just as with the z equation, we note that the type of solution depends on the SIGN of k squared, whether k squared is positive or negative, because of course it's the same k squared we were discussing before. If k squared is greater than 0, the solutions oscillate, and they are known as ordinary Bessel functions. If k squared is less than 0, then we remember that both the theta and z solutions in that case were oscillating, so the radial ones will have to be monotonic for everything to be self-consistent, as mentioned in class. And so in this case, the solutions would be what's called modified Bessel functions. All the physics applications we will look at involve ordinary Bessel functions, so we will always be looking at the case where k squared is positive. This is actually what was relevant for the Helmholtz equation in plane polar coordinates, as it happens. In class, we will look at the form of the Bessel functions, we'll draw them, we'll study their properties, and then we'll use them to solve physics problems. That's all.